In this lecture, you'll learn what are the different techniques that you could use to mitigate the overfitting problem in machine learning models, especially with neural networks. In the last lecture, we learned that dense neural networks are prone to overfitting, where the model is highly sensitive to the training data. It has a high variance error. There are some things we can do to mitigate this though. Let's see what they are. Overfitting can be prevented or largely mitigated using three main techniques: regularization, cross validation, or some kind of ensemble learning. And one variation of ensemble learning within neural networks is the use of dropout. Let's see what each of these are in detail. Because neural networks are prone to high variance, that is, the models tend to be overly complex, which work well on training but maybe less well on real world data. Regularization is a method by which we penalize complex models. You add a regularization parameter, and the more complex the model becomes, the more it gets penalized. This allows you to optimize towards keeping the model simple. Cross validation is a method by which you split your input data set into two distinct parts: the training data set and the validation data set. To keep our explanation simple, let's consider that we split the input data set into two parts, one for training and one for validation. We'll call it dataset 1 and dataset 2. If you train your model on dataset 1, you'll validate whether the model works well using dataset 2. You'll then probably train your model once again using dataset 2 and validate it using dataset 1. In this way, you'll get the best possible model. Dropout is a technique specifically used in neural networks in order to mitigate overfitting. Dropout essentially means that you'll purposely turn off certain neurons while you're training your neural network. Those neurons will not be responsive for a certain training phase. This will force other neurons in the neural network to learn the underlying features of the data. In every phase, you'll turn off a different set of neurons. Let's talk about regularization in a little more detail. Regularization is the mechanism that we use to penalize complex models, and in fact is very simple to implement in gradient descent. And with TensorFlow, they have some built-in libraries which just help you perform regularization on your neural networks. The idea behind regularization is that you add a penalty to your objective function, that is the cost function or the loss function that you use while training your machine learning model. This penalty basically increases the cost or loss within your model if the model becomes more complex. And how complex the model is measured as the function of the neuron weights. The addition of this penalty forces the optimizer to keep the model simple. If the model is simpler, the penalty will be lower. If it's more complex, the penalty will be higher. So it acts as a push and pull mechanism, pulling the model towards simplicity. In its very simplest form, when you're training your machine learning model, you'll simply measure how well the model performs on the training data set. And if once it performs well, you can immediately move it to production. However, this is not a technique that you'll use in the real world. In the real world, your model will have distinct training and validation phases. You'll train your model using some input data set, but you'll measure how well that model performs using an entirely different data set. This is a way to mitigate overfitting. With cross validation, though, you'll take it a step further. So you'll have a number of training data sets and you'll generate all your models using training data. You'll only measure how well the model performs using your validation data. So you'll select the best model based on validation data. Validation data is essentially data that the model has not seen during its training process. So it can't be overfitted to that data. And cross validation is where hyperparameter tuning is extremely useful. If you remember, when we spoke of hyperparameter tuning, we spoke of how we will design our neural network or machine learning models differently by tweaking the hyperparameters. We'll train each of these models on the same training data set, and then by measuring how well these models perform on validation data, we'll pick the model that performs the best. This is hyperparameter tuning, and it's used in cross validation and mitigating overfitting to the training data set. Neural networks typically use dropout as a mechanism to prevent overfitting to the training data. In every training run, you'll specify a fraction of neurons within your neural network that will stay off, and a different set of neurons will be chosen at random for every training step. This means for every step, the neurons that are on will be forced to learn new patterns, different patterns in the underlying data. They may have been off earlier, they're on now. So they are forced to learn new things at every step. Basically, when you use dropout, it means that your network configuration is different at every step. Different neurons are turned on and off for every step. The network configuration is different. Let's see this visually. Dropout is pretty important, and a representation of a neural network will help you understand how exactly it works. This is a dense neural network where the neurons in every layer are connected to every neuron in the next layer. There are lots of connections, which means there is a high risk of overfitting the training data. Let's say you configure the dropout parameter to 50% during the training phase. Dropout is applied only during training and not during prediction. This means that you randomly switch off 50% of the neurons in each training step. That means for every layer, half of the neurons are off. That means the other neurons which exist or are on in that particular training phase are forced to learn new features in the data. During training phase, this much simpler and more sparsely connected neural network is forced to understand patterns in the data. For every phase, the dropout will choose a different set of neurons. That means every training step will work with a different network configuration. An important thing to note here is that dropout is applied only during the training phase of the neural network. That's when we want to force the neurons to learn new features. During prediction, we'll use the full neural network. None of the neurons will be turned off. You can avoid overfitting models to the training data by using regularization, which imposes a penalty on more complex models. You can use cross validation, where you train on a data set but measure how well the model performs using a different data set. Or you could use ensemble learning. An example of ensemble learning is a dropout in neural networks, where you randomly turn off a certain percentage of neurons during the training phase so that the remaining neurons are forced to learn new features in the data.